So Friday we were talking about exponential growth functions. We started graphing them and recognizing them. Today we're going to alter them a little bit. We're going to change up our a so that they won't necessarily be starting at y equals 1 anymore. We'll have a different y-intercept. And then we're going to throw them into some word problems and see how we can apply exponential functions to real life. So the first thing we want to do is see how a affects our function. Remember that our basic exponential growth function looks like this. And Friday you were assigned homework that had a of 1. A was always 1. And so your y-intercept was always starting at 1. Now we're going to change that a little bit. So we're going to look at 3 different equations that all have the same b, different a's. So we'll look at what we would call the parent function. This is what we start with, 2 to the x, with a being 1. And then we'll make a 3. So we'll have y equals 3 times 2 to the x. And we'll have it be negative 3. So y equals negative 3 times 2 to the x. So this will give us a good look at how a changes the shape of the graph. Let's make sure we can tell that that's multiplication there, not just 32 to the x, because that would really mess us up. Now, based on what we learned Friday, we should be able to graph y equals 2 to the x fairly simply because we know that since a is 1, it's going to start with a y-intercept of 1, and it's going to go up by multiples of 2. Let's actually use this graph. This will let us go a little higher. Actually, I changed my mind. Let's use this one, because we're going to need to go back and forth. So we'll start by graphing the parent function y equals 2 to the x. So as we said, since a is 1, we know that we're starting at y equals 1. And what are we multiplying by as we go to the right? 2, because that's our b. So as we go to the right, we're going to multiply by 2, go from 1 up to 2, and from 2 up to 4, because we're multiplying by 2 each time. And from 4 up to 8. Okay? And what about as we go to the left? What do we do as we go to the left? Divide by 2. So we go down from 1 to 1/2, and 1/2 down to 1/4, and 1/4 down to 1/8. And so we have a nice curve that's going to approach y equals 0, but is it ever going to actually hit it? 9? It's going to hit 9 instead? Hopefully we put the German subtitles on this video. Alright. So then we're going to hit that y equals 0. So what do we call that line y equals 0? What do we call the line y equals 0? Starts with an A. It's called an asymptote. An asymptote. It's a line that the graph approaches but never actually touches. And it's called an asymptote. It's kind of like a limit that function is going to approach and get really close to and never actually hit. Make sense? Alright, let's try y equals 3 times 2 to the x. Now you had a question in your homework that should help you understand what that 3 is going to do to the equation. What are we going to do when we throw that 3 in the front? Yeah?
What if we start at y3 instead of y1?
Yeah, we'd start at 3 instead of 1. The reason we start at 3 instead of 1 is because on the y-axis, x equals 0, right? And if I put in 0 for x, what's 2 to the 0 power? 1. Anything to the 0 power is 1. So 2 to the 0 power is 1, and 1 times 3 is 3. So that's my initial value. That's where my function starts. Okay. Now what am I going to multiply by as I go to the right? Still by 2 because my base is 2. So I'm going to go from 3 to 6. And I would go from 6 to 12. Okay. Which I can't fit on this graph. What am I going to multiply or divide by as I go to the left? Divide by 2. Or multiply by 1/2. Either way you want to look at it. So we're going to go from 3 to 1.5. And from 1.5 to 0.75. Or instead of 1.5, we could look at it as 3/2 and 3/4 and 3/8. Now I want you to notice something about all these points. The y value here is 3. The y value here is 1. 1 times 3 is 3. The y value here is 2. The y value here is 6. 2 times 3 is 6. So all of our y values get multiplied by 3, which is what stretches this graph vertically. So that's why we'd call this a vertical stretch of the graph y equals 2 to the x. Because it's all of our original y values only multiplied by 3. Make sense?
Upside down.
Now for the upside down one. Okay. The upside down one is very similar. It just combines that multiple of 3 with a reflection over the x-axis. So instead of starting at 1 or 3, what are we going to start at now? -3. Because 2 to the 0 is 1, and 1 times -3 is -3. What are we multiplying by as we go to the right? 2. So we go from -3 to -6. -3 times 2 is -6. And from -6 to -12. And as we go in reverse, we divide by 2, and we go from -3 to -1.5, or -3 over 2, and -3 over 4, and -3 over 8. Make sense? So what we could do is we could see that these y values here, a y value of -3 is 1 times -3. Y value of -6 is 2 times -3. It's all of our original outputs from our parent function, from our 2 to the x, all of those points multiplied by -3. And so that negative is what makes it go down. It's what makes it go under the x-axis. We call that a reflection over the x-axis. And a vertical stretch, because it's still steeper than the other equation. So y equals 3 times 2 to the x. This was just a vertical stretch. Y equals -3 times 2 to the x is a vertical stretch and a reflection over the x-axis. So if I had to compare the two, those are the kinds of words I would use. That's the description I would give. Make sense? All right. Now, let's tie this into some real-life problems. So you're given another format in the book for writing exponential functions. Now, we changed our x, our input, to t because quite often exponential functions are mapped as an output over time. And so we use that t to represent time instead of using x to represent time because it's less confusing. Now the a still represents what a has always represented, your initial value. Okay. T represents time. But essentially what we've done is we've split the B into two different parts, 1 and R. R is called your growth rate. And we need to express that as a decimal. So if they tell us it grows at 2%, we need to convert that to a decimal 0.02. What the 1 does is the 1 maintains what you started with. See, if I just multiplied my starting value by 0.02, I would only get 2% of what I started with. And I don't want 2% of what I started with. I want 102%. Because I keep the 100% that I started with, and I gain 2% more. That makes sense? That's what happens when you put money in the bank. You keep what you put in, and then you gain the interest. And so you don't want to calculate how much you have in your bank account by just multiplying by, say, 0.03, because that will just tell you how much interest you've gained. Now together, 1 plus R is called your growth factor. Just like the B that we used before. So if we look at example 4, the owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984, and when he bought it in 1984, its value was $11,000. The value of the car increased at a rate of 6.9% per year. Write a function that models the value of the car over time. So let's take a step back. Let's look at this equation here. And basically we're just going to go in and substitute the values from our setup here, from our word problem, into this equation. So first of all, what's our initial value for this vehicle? 11,000. We're just going to base things off starting at 1984. And so 11,000 will be our initial value of the car. And what is R? 0.069. We base it off the 6.9% and we convert it to a decimal, 0.069. And then T is our variable for time. Not there yet. Okay, because we're just writing the function, so our function has to have an output variable and an input variable. So you can just simplify this to y equals 11,000 times 1.069 to the t. Okay, that's our function. That's what would allow us to find the value of the car during any time frame after 1984. So t has to represent years since 1984. So if we want to find the value of the car at a specific time, we have to figure out how much time it's been since 1984. So the second part of the question asks us to find the value of the car in 2004 when the auction was sold. How many years later is 2004? Did you say 3 years?
20 years.
20 years. Okay, much better. So that means we're going to take that 20 and plug that in for t. Now, I don't know anybody that can do 1.069 to the 20th power in their head in under, an hour. So plug that into your calculator. You can plug it right in just like that. 11,000 times 1.069, and then use that little caret button to the 20th. And what do we come up with? $41,777.92 rounded. Wow. So that's what the car was valued at in 2004. That's what he could expect to get at auction if it follows that pattern. Which means he made a profit of how much? Mm-hmm.
30,770.
$30,777.92. That's quite a profit, I think. I'll take it. Absolutely.
You can get another better car.
There you go. I don't know. That's a pretty nice car. All right, let's look at compound interest because this is where you're going to see it most often when you deposit money in the bank. Money in the bank earns compound interest, which means that at the end of the year, you get your interest added to your account. And so if you put in $100 at 5% interest, now you have $105. Well, if you leave that $105 in the bank, then next year you earn 5% interest, not just on the $100 that you put in, but also on the $5 interest you earned last year. Okay? And so you gain just a little bit more than $5. And then next year you'd earn 5% interest on what you had from the first 2 years. Okay, so that interest builds on itself. Make sense? Simple interest would get you just $5 a year. Compound interest earns you interest on interest. And so to model compound interest, we have to use an exponential function. And we use the same model we've been using. Y equals A, which would be how much you deposit, times 1 plus R, which would be your interest rate, to the T power, which would be how long you had your money in the bank for. So in example 5, we deposit $250 in a bank account that earns 4% annual interest compounded yearly. You don't make any deposits or withdrawals. How much will your investment be worth in 5 years? Now, why is it important that you don't make any deposits or withdrawals?
So the interest wouldn't be building on itself. It'd be simple interest then.
No, it wouldn't convert to simple interest, but it would change how much you had in there, so it would change how much interest you're earning. It would change your initial amount, and so it would invalidate the equation. Okay? This equation only works so long as our initial investment stays in there. We don't put anything in or take anything out to change that. So what's going to be our A?
$250.
$250. And what do we put in for R?
0.04.
0.04. That's our 4% converted to a decimal. And what's T? How long are we leaving the money in the bank for? 5 years. So all we have to do is calculate that out. What's Y equals 250 times 1.04 to the 5th power? And it asks how much will your investment be worth in 5 years. So there's the solution. How much interest did you gain? How much money did you make having your money in that bank account? $54.16. Make sense? Okay, that's exponential growth functions.